Alright, so multivariable linear systems. Basically what we're talking about is solving systems of equations that don't just have two equations, but have three equations, or four equations, or five equations, and an equal number of variables. One thing to take note of is if you have, say, three variables, then in order to come up with a unique solution for that system, you have to have at least three, you have to have three equations, okay? If you had three variables but only two equations, the best you could do is come up with some kind of a linear solution that would give you an infinite number of possibilities for your solution. So that's just kind of an introductory comment here. But what we're talking about is three equations with three unknowns. And what are we really trying to do? What are we trying to find? We're trying to find a value of each variable that when we put them together will satisfy every equation in the system. Okay? And this applies whether you have two equations with two variables or 10 equations with 10 variables. You're trying to do the same thing. Find values for each of those variables that when you plug them into the equation, it satisfies all of the equations. Alright? So in the example that we're going to work with today, the three equations with three unknowns, we are intersecting three lines in space. Okay? There are three different lines in space. And as you can anticipate, when you have three lines crossing in a three-dimensional space, it's not going to be uncommon for there to be no solution. In fact, if I asked all of you to write down three equations that had an x, a y, and a z in it, and we tried to solve those as systems of equations, chances are most of them would not have a solution. Okay? Because a no solution can happen a number of ways. Right? In two dimensions, the only way you got a no solution is if you had parallel lines. So it wasn't as common to run into that. But here you could get it a few different ways. One is to have parallel lines with two of the three lines, or all three. But if two of the lines are parallel, or if two of the lines are skew, alright? Can anyone remind us what skew means?
When like lines are like in different planes. So like one's like this and one's like here.
Yeah, two lines are in completely different planes. So they are not parallel, but they're not intersecting either. Okay? And then another common occurrence is you have all three lines and they do intersect, but they don't intersect at the same point. They intersect each other at different points. Alright, and just so you can see kind of what it would look like, when there is a solution, there will be this one point, x, y, z, in three-dimensional space where all three of the lines coincide. However, this last thing here, all three lines intersect each other at different points, is going to be something like this. Okay? These two intersect up here, these two intersect over here, these two intersect over here, but they don't all three intersect at one point. So there's no solution to the entire system. Now,
Sorry, do you mean to say or after skew?
Yeah.
oh, yeah, thanks. There we go, thanks. Alright, so let's talk about how to solve a system of three equations with three variables by elimination. Okay, elimination. Now this method, it's kind of a variation of something called the Gaussian method or Gaussian method. Only in the sense that the same guy came up with both of them.
Wait, is that from bio?
Remember the Gaussian model was our bell curve. Okay, so he kind of came up with both of them. Carl Friedrich Gauss came up with, he was a pretty accomplished mathematician. back in, I think, the 1800s or 1700s. But it's kind of a variation of that. You might also hear people refer to this as a linear combination, or they might call it adding multiples of equations. There's a couple of different names for this, but elimination is a common one. And the idea is this, okay? We're going to take the three equations and we're going to pair them up. And obviously, if we're going to compare pairs or combine pairs of equations twice, we're going to have to use one of the equations twice. Alright? So we might combine the first and second equation and then the second and third equation to get two pairs of equations. What we're going to do though is we're going to eliminate the same variable both times. And what that's going to end up giving us is two equations with only two variables. And you see, this is why I said we're skipping sections 1 and 2, but this essentially is what sections 1 and 2 covered, was solving two equations with two variables. So you'll see that done here in the middle, in the midst of that. Okay? So let's consider this system here. And we'll talk about what we mean by combining the equations. Alright? When we combine equations, what we're doing is we are adding one side of one equation to a side of another equation, and then we're adding the other side of the first equation to the other side of the second equation. So in other words, if I were to take these two equations right here, and I were to combine them, I would simply add the like terms together. So I'm adding the left side to the left side. I'd get 3x minus 7y plus 8z equals 26. Now, that was not incredibly helpful because we still have three variables.
So
Okay?
you can multiply the bottom one by -2.
Okay, and you're obviously trying to eliminate which variable?
X.
We're trying to eliminate x. Okay? And in fact, this one, it actually is easiest to eliminate x. So let's go ahead and do that. We're going to use these two equations as a pair. And we're going to multiply this third equation by a -2. So I'm going to copy the second equation, 2x minus 5y plus 5z equals 17. And then I'm going to multiply the third equation by a -2. So I have a -2x plus 4y minus 6z equals a -18. Okay? So notice here I'm multiplying by a -2. Now I'm adding them together, and this time it was actually helpful because 2x minus 2x is 0. Okay? As I add the other things together, I get a -y, a minus z, and that equals -1.
Could you just add the first equation and the third equation? Yeah.
We actually will do that. Okay? Ellie?
Did you just choose the
First and
-2
third?
to eliminate the x, or did you do that because
That's what I was
it's
thinking.
-2 in the first one?
I did it just so I could eliminate the x. Guys, the whole point of this is you have to eliminate one of the variables. Alright? The easiest way, obviously, that someone saw was to say, hey, that's a 2x, that's a 1x, so if I multiply that by -2, my x's will cancel out. The only thing is you got to remember you got to multiply everything in this last equation by that -2 to be fair. All right, but that's why we did it. Now, we could have tried to eliminate the y's. I would have had to multiply like the second equation by 2 and the last equation by a -5. And I would have gotten a -10 and a +10y. Or I could have taken this one and multiplied this equation by 3 to get a 15z, and this one by a -5 to get a -15z, and I would have eliminated the z's. You can do any variable, but as you guys work on these, you'll see cases where it's a little easier to eliminate one as opposed to the other, okay? So I'm going to take our result here, and I'll put it there. All right, we now need a second pair. All right, and Yash recommended using the first and third equations. All right, and that's a good idea because we have a negative x plus 3y plus z equals a negative 2, and we have a positive x minus 2y plus 3z equals 9. The nice thing about this one is that it's already set up for us. We don't have to multiply anything in order to just add them together and eliminate the x's. Alright, so the x's cancel out to 0. We have a y plus 4z equals 7.
And then you
The y and the y cancel out once you add both together.
Well, yeah, it will end up. Alright, but notice what we have now. We now have two equations with two variables. Alright, let's try to focus. Alright. We now have two equations with two variables. I'm going to copy this one over here. Okay. And you'll notice this one, we can again use elimination to, with these two equations, eliminate one of the variables so we can solve for the last one. Alright? In this case, you'll notice the y and the minus y are set up nicely so that we can add those together. And we get 3z equals 6. So z must equal 2. Okay?
Yes.
Yes.
Maybe.
Alright, now what we have to do, we're not done. We've only found a third of our final answer.
So now you put the z in.
Yeah, now we have to do a process called back substitution.
Right.
Now, understand that these equations, all the equations you see now, the y is going to be the same value, the x is going to be the same value. So it doesn't matter what equation you use. As long as we have a z in it, if we want to figure out what y is, we can plug in 2 for z. So I'm going to use this y plus 4z equals 7. I could use the negative y minus z as negative 1. But if I plug in a 2 now, I have y plus 8 equals 7, which means y has to equal negative 1. Okay, y has to equal negative 1. Now I use back substitution again, and I'll use it with this third equation here. Okay, x minus 2y plus 3z equals 9. Okay, I now know that z is 2, so 3z is 6. I know that y is negative 1, so the minus 2y equals a plus 2. Alright, so I now have x plus 2 plus 6 equals 9, so x has to equal 1. And that means that my solution is the point 1, negative 1, 2.
Point?
Do you want us to put our answers like
three.
that?
Okay.
Oh.
It's a point in three-dimensional space.
How would
So-
how would you draw that point?
How would you draw that point? You have to use the three-dimensional
Oh, I've seen that before.
thing.
I
So
like those.
this is, people draw them differently. You could draw x like this, and then y is kind of coming from the back like this. Alright, that's the negative y, this is positive x, negative x,
Wait, why is that negative?
positive y, because that's in the back.
Oh.
and it's coming towards you, towards positive y.
So
Yeah.
it's 1.
It's hard to visualize.
So you gotta.
It makes sense
imagine
if you
like a
like close
cube.
your eyes and you like.
So if I were to graph this, I'd go positive 1 on the x-axis, and I kind of draw it parallel. Alright, so now I'm kind of over here, and then it's negative 1 on the y, so that's going to be back here. So I kind of go like this. That's going to be there. And then up 2 on the z-axis. Okay? So I have to measure, you kind of measure with your fingers or whatever, that high. And from here, we got to go that high. Okay?
Why, Jesus?
So
Why would you repeat
there's our solution point.
Do not.
This way, if you take college, if you take multivariable calculus in college, you'll have to graph stuff in 3D. It's a whole lot of
I
fun.
would take that.
So it actually is fun. I enjoyed that part a lot. It actually
That's
really
easier
helped.
than English.
I was a horrible. I'm still a horrible artist, but
Helps.
I was an even worse artist before I took Calc 4 in college.
Because then now
And
you-
after that, then I actually was able to draw some 3D stuff pretty cool.
X and Y?
So, anyways, what I want to do though is look at something here. Does everyone understand how we got this solution?
Yeah.
Yeah.
Get two different pairs, eliminate the same variable. Now you're down to a system of two equations with two unknowns. Solve it, and then back substitute. All right. If I were to write this, however, as a system of equations, all right, x equals 1, I could write as 1x minus, 1x plus no y's plus no z's would equal 1. Do you agree that's the same thing as saying x equals 1?
Yes.
Alright, good. Now, I could also say that no x's minus 1y, or I'm sorry, plus 1y, I'm messing this up, plus 1y plus no z's is going to equal a negative 1.
If you say so.
Okay?
Oh,
So y is negative 1.
because y isn't back.
And lastly, z equals 2. So I could say that that is no x's plus no y's plus 1z will equal 2. Okay?
Do we have to write anything like that for a test?
No, not in your answer, but what we're about to look at is to apply this to matrices. Okay? The end result, once you've solved a system of equations with matrices, is going to be a matrix that looks like this.
Don't you like do like row by row and column by column or something?
Okay? And we're going to talk about this specifically here, but you see the comparison? An x plus no y's and no z's equals 1. No x's, a y, no z's equals negative 1. No x's or y's plus 1z equals 2. Okay?
But then
Those are the same idea.
on like the ACT and the SAT, then they'll have another matrices next to it, and they'll be like, "What is the plot? Like, how do you?" Like,
We're going to get to that in later sections in
It
this
takes
chapter.
so long too, doesn't it? 'Cause you have to do the whole thing.
Multiplying matrices takes a while, but we're not going to get to that for.
No, I know it's simple,
little
but it's
bit.
like, isn't art like isn't there supposed to be like a fast trick to all ACT questions and SAT questions? So then,
ACT and SAT? Oh,
you know,
if
like
you
you're
have
not,
multiple choice, actually there is, you can get the answer without having to do the entire thing, but we'll talk. Alright,
Then you go
we'll get to that stuff later though. Let's talk about what a matrix is though first. Alright, you do not need to write down all of this, alright? I wanted to show this to you and just highlight a couple of things. First of all, understand that a matrix is a rectangular array. An array is just an arrangement, okay? It's an arrangement of numbers in a rectangle, okay? This rectangle is always included in these brackets, okay? we write the values of the matrix in brackets. Okay, the rows go across and the columns go up and down. But another thing I want you to pick up on now, even though we won't use it as much until the next section, but an M by N matrix. I'm not sure what exactly that was. Let's try this again. There we go. Has M rows and N columns. Okay. Now we name matrices with a capital letter, and then you'll see two little numbers next to it. Okay. Those are the dimensions of the matrix. So what this is telling us is that this matrix, and it has two columns. All right. If A were a 2 by 3 matrix, then it would only have 2 rows and it would have 3 columns. That's going to be particularly important later as you look at matrix multiplication. Okay? So this is what a matrix is. It's just an arrangement of numbers. Okay? Now, let's talk about a couple of matrices that we're going to use that relate to a system of equations. Here's a system of equations. There are two different matrices that we could deal with, and I would like you to know these terms, okay? Here's the system with our x's, y's, and z's all written out. Okay. And one thing is, before you write any kind of a system in a matrix form, you need to have the x's, y's, and z's, or however many variables you have, in order, okay, and in the same order in all three of your equations. And you need to have these constants on the other side of the equation, okay? So you'll notice I've got x, y, z, and the numbers on the other side. In the augmented matrix, what we've done is we've taken the coefficients of x, of the x's, and we've made that our first column. So you could kind of look at that as the x column of the matrix. And then we take the coefficients of the y's. We had negative 4y in that equation, 3y's there, no y's in the last equation. So we make a column out of those. Then we take the coefficients of z and we put those in their own column. And then the constants are their own column as well. Alright, so those are just numbers.
We put the dots in.
Yeah, why do you use the dots?
Well, the dots help us remember where the equal sign goes. Those are not required, but they can be helpful. Okay?
So the system, its matrix, would that be the same as the thing you did before with solving a matrix and it was like 0x plus?
Yes.
The same thing.
We would be given a system like this, and the first thing that we're going to do is write it as an augmented matrix.
Oh, and
then our goal is to get to where it's 1, 0, 0, something.
And that's the coefficient matrix.
Well, no, that'll be the solution.
Okay.
The coefficient matrix is actually used in writing our system in a different way. Okay? The coefficient matrix does not include these constants on the other side. It's just the coefficients of the variables. And it has other applications. Okay? One of them is to rewrite this as a matrix equation. Okay? Now, this is the coefficient matrix, but I could rewrite this whole equation as this. I could multiply it by this 3 by 1 vector, x, y, z, and have that equal to the constant matrix 5, negative 3, 6. Okay? This equation right here shows us this entire system. And then there is a way to get an inverse matrix that we could then multiply both sides of the equation by. Multiplying by the inverse will get rid of that, and then we can get our answers. Okay? That's a different way of solving the same system.
I'm assuming we'll do later.
We might do a little of that later, but not a whole lot. Okay? But I want to focus in on our augmented matrix we're going to use now, because that is kind of the starting point for what's known as the Gauss-Jordan elimination method. Okay?
Do I need like a, you think I need a new page?
It'll probably take, it'll take more than that. Okay? Now, this method
Can you what, Jesus?
can take
I think you've done enough.
a little bit of time, okay? Understand though that essentially we're doing the same thing we did using elimination. The nice thing about this though is that we don't have to write our x's, y's, and z's all the time. Okay? Because we have them arranged in a matrix, we know that anything in that first column is going to have x's. Anything in the middle column is going to have y's, anything in the third column is going to have z's. And anything in the last column is on the other side of the equation. Alright, so we don't have to write down all the x's and y's and z's. Okay. So let's take a look at what our goal is here, and then we'll look at an example of how we can get there. Okay? Our goal is what's known as a row-reduced echelon form. You'll see it abbreviated RREF. Okay? Row-reduced echelon form. And you'll recognize this from earlier. We had a 1, 0, 0, then some number. And then 0, 1, 0, and then some number. And 0, 0, 1, and then some number. And once we got it here, then we could say, oh, x equals whatever a is, y equals whatever that b is, z equals whatever that number c is. Okay? That's our goal.
Why is that our goal?
Because that'll tell us exactly what these answers are.
Oh,
Okay? Now, there is a way that your book shows, it's called just Gaussian elimination. And instead of row-reduced echelon form, it's just echelon form. Or row echelon form, just REF. If you see that, it's REF. That one requires you to kind of combine what we're doing here with back substitution. Basically, we'll just use row echelon form until we get this 1001C, then we'll back substitute it. So basically, it doesn't try to get these to be zeros. It only does this part, and then it back substitutes into whatever that is, and to get your x and your y. I don't care for that. It's not too hard to get those other zeros, so that's why I like just doing it this way. Okay? We're doing row-reduced echelon form. Echelon, for those of you not familiar with that word, echelon just means a level. Okay? Or a tier, T-I-E-R. You know, if you have different levels of things, you can kind of see a stair step here that it's on echelons. Okay? Now, here's the basic procedure. Let me show you real quick. I'm going to jump down below here, and then we'll take a look at this stuff here. If I were to try to solve this system, it's the same system as what we had earlier. So we know the answer is what, 1, negative 1, 2?
Yeah.
Okay. The first thing I would do is we're going to write the augmented matrix. Okay, notice our x's are all first, our y's are all second, then our z's and our constants are on the other side. So the augmented matrix here is going to be the first column's -1, 2, 1. The second column is 3, -5, -2. The third column would be 1, 5, 3. And the constant column is -2, 17, and 9. I don't usually put the dots in. If you tend to be sloppy, first of all, don't be here, or else this is going to be a disaster. Okay? If you have sloppy handwriting, or if you don't, for some reason, you don't know what those blue lines on your paper are for, they're for you to write along. You need to start using them in this section, okay? If you're sloppy here, you're going to make little mistakes all over the place. It's going to drive you nuts. Because this is the kind of thing, this whole process, if you make a mistake on like the first section, or the first step, you know, there's no recovering from that. And finding your mistake is nearly impossible. Okay?
Is your partial credit? New quizzes in this work?
Yeah. But that won't remove the headache. So, anyways, we get this matrix here, and again, remember our goal is to get 1, 0, 0, 0, 1, 0, 0, 0, 1, okay? So how are we going to do this? First of all, we're going to start in this first column. We're going to get the 1 where it's supposed to be. So we want to get the 1 in this top left corner here, okay? Then we're going to work to get the zeros in that column, okay? Zero out the rest of the column. The reason why that's important is then when we go to the next row, we're going to get the 1 here, and then use this row here to get zeros there and there. But if these aren't zeros, it's going to mess up this one, okay? And you could be going back and forth getting your 1s and never actually solve anything. Okay, so you get the 1 in the column, then 0 out the rest of the column. Then move to the next column. Get the 1 where it's supposed to be, 0 out the rest of the column. Then move to the last column, or the third column, get your 1 where it's supposed to be, and then 0 out the rest of the column. Okay, and once you get the hang of it, it's really not a hard process. It's just something that you have to do very carefully. But the nice thing is it works pretty much the same every time. Okay? Now let's understand what we're able to do in order to get to where we want to go. First of all, you can interchange 2 rows. What are we essentially doing if we're just interchanging 2 rows?
Changing the, like using two systems.
I have a question. If we like eliminate like we did on the first slide, we'll get the row reduced form.
You can, yeah.
But like we'll always get it.
Yeah,
So then
if you wrote it that way. This, I think, will end up being easier once you get the hang of it. Trust me. Okay? Each row represents an equation, right?
yes.
Does it matter which order we put our equations in?
No.
No. So when you're interchanging 2 rows, you're just writing the equations in a different order. Which is actually what I would do first of all here, because you'll notice I have a 1 here. I'm going to swap row 1 and row 3. Okay? So I'm going to make it 1, -2, 3, 9 in the first row. The second row is still staying the same. And I'm going to put -1, 3, 1, -2 down here. Okay? Swap R1 and R3. Okay?
Interchange them, right?
What?
You switch them.
I switched them. Yeah. Swap, switch. Okay? So now I have my 1 in place. Now, the other 2 things. We're able to multiply an entire equation by a number, right? So we could multiply a whole row by a number. For instance, I could multiply an equation by 2 on both sides. Alright? So that's what I'm going to do. That's what I can do here. And then thirdly, this is what we were doing with the elimination, these last two here. I can add a multiple of a row to another row. Okay? Just like we added two equations together, I can add rows together. So, yeah, for example here, now that I have my first row is going to stay the same because I have my 1 in place, I want to get zeros here and here. Okay? So let's think about this. All you really need to look at is this number here. I have 2. And I'm going to do something with row 2 and row 1. So what do I need to do with row 1?
1 times negative 2 plus root 2.
That's right. We're going to multiply that row 1 by a negative 2. So row 2 minus 2 row 1. 2 minus 2 is 0. Negative 5 minus 2 times negative 2 is a plus 4. So negative 5 plus 4 is a negative 1. Right? 3 times negative 2 is negative 6. So 5 plus a negative 6 is a negative 1. 9 times a negative 2 is negative 18. 17 plus a negative 18 is a negative 1. Okay? So I got my 0 there in the second row in the first column.
So you multiply the top one, you multiplied the top column by negative 2.
Top row, yep.
And then row, row by negative 2, and then you basically found the resultant equation, and that's your second row.
Well, no, I multiplied the top row by negative 2, and then I added it to the second row to get a new second row.
But then, shouldn't the top still be,
The top is still the same, okay, but I changed this second row here.
okay.
Alright?
Will you always do row 2 minus the coefficient of the first one in the second row?
It'll often be something like that, yeah.
Will you ever have to? Oh no, because that'll always be 1.
Yeah.
Couldn't you, like, to get the third row?
What if it's not
row
always
3
1?
plus row
Like this one we switch
Yeah.
it.
Well, with this one here, row 3, again I'm going to use row 1, but notice I have a negative 1, I just have to add the 1.
Plus.
So it'd be plus row 1. That's a 0. 3 minus 2 is 1. 1 plus 3 is 4. Negative 2 plus 9 is 7. Okay? And that's it. And then we could keep going. Now we would get a 1 here, 0 out the second column. So we'll pick it up there tomorrow. Alright? See ya.
Alex, good talking.